Good morning, everybody. Thanks for coming. Today we have the honor Kavli Institute for Cosmology in the University of Cambridge since 2016, and a professor in experimental astrophysics in the Cavendish Laboratory in the Department for Physics in Cambridge. His career started with a PhD at the University of Rome, La Sapienza, and University of Florence on secondment to the Steward Observatory in the USA, in Arizona, in '96, followed by 2 years postdoc in Max Planck Institute for Extraterrestrial Physics in Garching. I have a problem with that word. Then he got a position as an astronomer, then as a senior astronomer at Cetri in Florence, and then at the Astronomical Observatory in Rome until 2012, when he moved to Cambridge. In 2016, he received an ERC advanced grant called Quench, aimed at investigating the mechanisms responsible for quenching star formation in galaxies and transforming them from star-forming system to quiescent systems. In 2008, he received the Knight of the Italian Republic, so the Commendatore dell'Ordine della Stella d'Italia, and he is first or second editor of 3 books, author of more than 360 papers, including Nature and Astronomy and Astrophysics Review. This year, I make you know, if you don't know, there's a review on metallicity. He's the first author with another one, with Pier Manucci. And with his papers have close to 30,000 citations, so he has an age of 95. He has been lecturing in advanced schools quite often and also invited reviewer in many occasions on his many fields of research in extragalactic astronomy. He has supervised about 20 postdocs and research fellows and 31 PhDs, mainly in the universities of Cambridge, Rome, Florence, and in Garching. He has participated or participates still in many international committees. I'm just taking some of them. Since 2015, he belongs to the organizing committee of the cross division of the IAU, working on the supermassive black holes feedback and galaxy evolution. He's scientific council of the Italian embassy in London. He's member of the International Science Advisory Board of the Japanese Space Agency. In the European Astronomical Society, he's been member of the working group on the future of European space astronomy, and concerning also planification and astronomy, he's member of the committee for planning of the VLT Large Telescope in the 20s. For ESO, in the Astronet working groups for wide field spectroscopy and for the roadmap as well, in many time allocation committees for LBT, Chandra, IRAM, ESO. And concerning instrumentation, he's chair of the RICH board, which RICH means Radio Experiment for the Analysis of Cosmic Hydrogen, since this year. He's the project scientist and chair of HIRES for the ELT. He's co-PI project scientist and member of the board of MOONS at VLT. MOONS comes from Multi-Object Optical Near-Infrared Spectrograph. He is member of the instrument science team of the James Webb Space Telescope instrument NIRSPEC, and he has been PI of the 2 main ESO large programs, AMAZE, which is assessing the mass abundance redshift evolution, and CLEVER, KMOS lens velocity and mission line review. He has been active in multiple areas in observational extragalactic astrophysics. I'm just picking some of them with some of the main important results among many. For instance, concerning the unified model synchronuclear medium host galaxy of AGN, it was a discovery of a large population of heavily obscured AGN since the very early results in his career. Also, obscured supernova, wormhole galactic medium, the formation and evolution of dust, and the metallicity evolution throughout the cosmic epochs, with the discovery of supernova origin of dust at height Z, and the first measurements of metallicity gradients at the redshift greater than 3, for instance. In the galaxy formation in the early universe, when early means as early as redshift greater than 7. in a galaxy transformation and quenching, which you know from the ERC, and also, last but not least, in galactic outflows with the first discovery of star formation in galactic outflows. And this is exactly the subject of today's talk, which is about the effect of outflows in the evolution of galaxies. So we are very pleased to have Professor Roberto Maiolino here with us. Thank you very much.
Thank you. Thank you for a nice introduction, and thank you for the invitation. I've been, I think it's 15 years I haven't been in Granada, so I'm very glad to be back here. So indeed, I have various science interests, and lately I've been particularly interested in galactic outflows and the effect that they may have on their host galaxies, both in terms of negative feedback and positive feedback. And I will shortly summarize, give an overview of this area, and present also some of the results of my group and my collaborators. So feedback. So let's first summarize why we need feedback, especially negative feedback in galaxies. And this is a very famous kind of diagram that is often shown, illustrating one of the main issues in galaxy formation and evolution. So what you see here in dashed is the mass function of dark matter halos according to theory and cosmological simulations. And instead here you see the observed stellar mass function of galaxies, okay, which are hosted in these dark matter halos. And you see that the shapes are completely different, which means that the formation of stars in different dark matter halos is actually is not uniform. In particular, at high masses, the formation of stars is quite, in galaxies in massive halos, is very inefficient, as well as at low masses. And this can be seen more clearly by taking the ratio between these two functions, okay, which is shown in this diagram here. So this is the stellar to halo mass ratio. And you see you have a peak of efficiency of formation of stars around in halos, which are masses of around 10 to the 12, and the efficiency drops steadily at low masses and at high masses. And one of the hottest topics in astrophysics is to understand why is that, okay? And a common tendency is many models and theories ascribe this the decrease of efficiency of star formation in low mass halos to feedback from star formation, and particularly by supernovae, typically. And while at high masses, the role of AGNs and quasar feedback, especially in both cases in the form of outflows, has been one of the main mechanisms which has been proposed for this feedback, negative feedback phenomenon. And I've put question marks because I like to be critical and to be, how to say, to scrutinize all of these often commonly accepted scenarios, because I believe there is both mechanisms, the fact that the feedback produced by both processes is still to be properly assessed, and there are still a lot of open questions. And so I will try to give you an overview of what we understand and also of what we do not understand. Okay. Now, an even more extreme effect of the regulation of star formation to feedback is the so-called quenching of galaxies, which is often invoked, of star formation in galaxies, which is often invoked to explain the so-called bimodality of the galaxy population. So this is another well-known diagram where you have the star formation rate in galaxies as a function of stellar mass, and this is the distribution of several hundred thousands of galaxies taken from the Sloan digitalized survey. And what you see here is that most galaxies tend to have, most star-forming galaxies are distributed along a relatively tight sequence, which is sometimes called the main sequence of star-forming galaxies. This is where most star-forming galaxies evolve. And then you have a secondary population, which at the given mass, they have a much lower or essentially nearly absent star formation. And one of the key questions in astrophysics is to understand why at some point these star-forming galaxies stop forming stars and they essentially move from the so-called main sequence to the so-called red passive quiescent region. Okay, so what is the mechanism that at some point halt star formation or prevent gas to form stars? Now, understanding why some galaxies have more or less formation of stars, in the end translates into understanding their gas content and the properties of their gas content, because we know that the formation of stars is tightly connected with the presence of cold gas, which is the fuel available for forming stars. Okay, and this is essentially embedded in the so-called Schmidt-Kennecat relation, which is relates the surface density of cold gas with the surface density of star formation. So the understanding why you have star formation or you don't often translates into understanding why some galaxies have gas and why have more gas or less gas available for forming stars, or even within given the same amount of gas, why in some cases the gas is this gas is more efficient in forming stars, and in other cases is less efficient. Okay, and of course this gas is the galaxies do not have fixed. One should take into account that galaxies do not have a fixed amount of gas, fixed reservoir of gas. They keep accreting gas from the intergalactic medium, from the circumgalactic and intergalactic medium, and we know very well this for our own galaxy. This the so-called G-dwarf problem, if you are aware of that, was the first indication that the galaxy has been continuously accreting gas from the circumgalactic and intergalactic medium, and now we see also the so-called H1 high velocity clouds, which are neutral gas clouds which keep orbiting the galaxy and accreting on the galaxy. And we see also these in several other nearby galaxies, direct evidence of accretion of gas from the intergalactic medium, and there are many more indirect evidence that galaxies throughout the cosmic epochs keep accreting gas. Okay, now so understanding how the galaxies, this formation of stars in galaxies can be suppressed or even quenched, implies typically the various models or scenarios invoke three typical mechanisms. Okay, one is simply, so if you want to stop, one way to stop star formation or to reduce the formation of stars is to remove gas, so what is available, the fuel available for star formation, and this is often what is done through outflows, which is the topic of this presentation. Okay, and the outflow can be driven by accreting black holes, by strong radiation pressure, or injection of energy, or by supernova, or through radiation pressure from young stars. Okay, there is another mechanism that I will not have time to discuss, which is of course ramp pressure stripping in dense environment of galaxies falling into, for instance, galaxy clusters, which would deserve a totally additional presentation, which I don't have time now to give. Okay, so for the moment we'll in this presentation I will neglect the environmental effect, but I'm glad to discuss this later on if you want. The other mechanism is still not to remove gas, but to prevent further accretion of fresh gas onto the galaxy. So if you do so, of course, the galaxy has its own reservoir of gas to use for additional star formation, but when that's over, at that point, the galaxy dies as starvation. Because of starvation, it doesn't have additional fresh gas to foster fuel additional star formation, and this is this called starvation scenario. Sometimes you may have heard about this as also as strangulation, which is more appropriate in the environmental effects, but again, which I don't have to discuss. The other possibility is that you neither prevent accretion of gas, but that for some reason the gas which is available in the galaxies is made ineffective in producing stars. And this can happen because of injection of turbulence or heating. If you make the gas very turbulent or very hot, its efficiency in producing stars it decreases a lot, and therefore it can still have a gas-rich galaxy, but which in the end forms a few stars. So one of the challenges is to understand what are these, which of these various mechanisms is dominating. Okay. Now, let's first focus on the low mass regime, okay, where star formation feedback is supposed to dominate, okay, and particularly the injection of energy by supernovae. Now, we know that there is evidence for this is well known that there are star formation driven outflows in most star-forming galaxies. This is the famous galaxy M82, where you have these spectacular outflows at different levels. Essentially, all star-forming galaxies have some evidence of more or less outflows, which typically correlate with the star formation rate. Now, this has been observed by various teams, including here in Granada, and I'm showing here an example of a result from SARA here, and you see that this is the ratio of the velocity of the outflow with respect to the escape velocity, and you see that in a good function of galaxies, the wind is strong, is fast enough to essentially exceed the escape velocity, and therefore meaning that we leave the galaxy. So this is indeed an effective way to remove gas out of the galaxies and therefore reducing star formation. This is a local example, and this is a similar study at higher redshift, where these teams compare the width of the nebula lines with the circular velocity. So the circular velocity is giving you a measurement of the escape velocity, while the width of the nebula lines is a sort of indication of how fast are the outflows. And you see that these lines divides gas which is gravitationally bound to the galaxy or to the halo with respect to gas which is actually unbound. And you see that also at higher redshift, in a number of galaxies, especially those with low mass, the outflows can again exceed the escape velocity not only of the galaxy but also of the dark matter halo, implying that these star formation driven outflows can be really effective in removing gas out of the galaxy and therefore suppressing star formation. Okay. However, well, first there is still the fact that a large fraction of, going back to these diagrams, a large fraction of galaxies have outflows which are not that effective, meaning that the gas remains gravitationally bound to the galaxy and therefore will not escape the galaxy and therefore will still be usable for additional star formation. And the other interesting aspect is that when you estimate the so-called mass loading factor of the outflow, which is the ratio between the outflow rate of the outflow and the star formation rate, this is often less than unity. So you actually, meaning that there is typically, except maybe in some powerful star forming systems, which is still debated how effective it is, but in many galaxies, the rate at which gas is removed through outflows is much lower than the rate at which is being used by star formation, which means that these outflows do not seem to be so effective in removing gas. And indeed, most models would like to have this mass loading factor around 1 or even higher in order to properly regulate star formation. So the fact that we see that this loading factor is often less than 1 is indeed a problem, suggesting that we may have a problem in using the supernova-driven outflows in regulating star formation. Okay, and indeed, this has been highlighted even more by recent detailed numerical simulations, cosmological simulations of the effect of supernova-driven outflows in galaxies. And this is an example of the our simulation team in Cambridge by Smith and Deborah Sijaki. And what you see here is, again, the stellar to halo mass ratio is this bell-shaped function that you have seen a few minutes ago, but focusing on the low mass end. Okay, so this is what is essentially observed by various or inferred by various teams, and this is what these detailed simulations, zoom-in simulation with where all the possible realistic physics of the supernova feedback has been implemented, and you see that essentially these galaxies keep forming stars. The amount of stars that they form is orders of magnitude higher than what you would need to match the observations. So the best of our knowledge of the physics that you can implement in the most detailed hydrodynamical simulations, you fail to reproduce what you see in galaxies. So this common knowledge that star formation-driven outflows are all enough or totally solve the problem of understanding the reduced efficiency of star formation in low-mass galaxies doesn't seem to work very, very well with the current understanding that we have. One possible solution that people have invoked is that, this is an example of these detailed cosmological simulations with zoom in. Okay, so here you have this galaxy where you have on this side the distribution of gas density, on this side the gas temperature, and this is the view face on and this edge on. And you see that all of these explosions here are individual supernovae that they pile up in the central region. As you see, they combine and produce this supermassive, very hot outflow, which is indeed harassing the galaxy a lot, is producing a lot of damage to the galaxy. But you see all of these holes in the gas are due to these supernova explosions that combine together, especially in the central region, remove gas. But you see that in the end, although dramatic, it does look dramatic, in the end, the bulk of the gas in the disks will remain there. It's not really that effective in affecting the global, the bulk of the gas, the dense gas in the galaxy. Okay, but most of the gases remain self-shielded and stays there. The main problem is that essentially in these systems, the energy injected by supernovae essentially doesn't couple very well to the ISM. It leaves the galaxy along the direction of least resistance, typically perpendicular to the galaxy, and leaves the rest of the dense gas mostly unaffected. So one possible solution that people have invoked is that also that even in low mass galaxies, weak or faint AGNs can contribute to the quenching of the suppression of star formation. And there's been a number of papers recently claiming the presence of AGNs in low mass galaxies. So we are talking about masses with masses of 10 to the 8, 10 to the 9 solar masses in stars. And this is an example from the Manga survey where they show that you have these low mass galaxies with these stellar velocity fields, while the gas velocity field, it doesn't follow the same pattern, but it is perpendicular, suggesting that this is outflowing gas. And the diagnostic ratio, this is the so-called BPT diagnostics that differentiates between AGN accretion, black hole accretion, that is AGNs, and star formation. Many of these have diagnostics typical of AGN. So they suggest that the AGN in these galaxies is playing a role in removing gas and heating gas and therefore suppressing star formation in these galaxies. However, it's still the fraction of AGNs in these dwarf galaxies is still small, and in the simulation they show that it's still even AGNs are not that effective. So this is how you suppress star formation in low mass galaxies, and in some cases how you totally quench star formation by producing the low mass end of the passive population of galaxies, I think is still an interesting, very interesting open problem. Now let's go to the high mass regime. Okay. Now the first here is where people have invoked that the presence of AGN or quasar-driven outflows play the main role in suppressing the star formation efficiency in this system, and they're actually producing the population of massive and passive galaxies already in place, not only locally, but already in place at high redshift. Now, to begin with, let me show you a recent result that may may indicate that actually there may be a different, and even yet a different mechanism. So this is a powerful star-forming galaxy. It has a star formation rate of about I think 4,000 solar masses per year. So one of these crazy, extreme star-forming starburst galaxies. And it's a lensed galaxies discovered by the SPT South Pole telescope at redshift 5.6, which we observed with ALMA last year. And these is our various nebular lines. So this is a lensed galaxy. So you have the central lensing galaxy, which is an elliptical, nearby elliptical, while these are three images of the lensed galaxy, okay? And this is a spectrum extracted from ALMA of this northern component, which is the brightest of the three. And you see that, well, the first thing is that you infer that it's so compact the emission, okay, of associated with star formation, that you infer surface density of star formation rate, which is something like 5,000 solar masses per year per kiloparsec squared. Now, this is an amazingly high density of star formation and is about 5 times higher than the so-called maximal starburst. Maximal starbursts are starbursts in which, according to theory, the star formation rate is so high that the radiation pressure by new stars is so strong that essentially expel all of the gas and it should prevent any additional star formation. It's the so-called essentially Eddington limited star formation. That is, beyond that star formation rate, the radiation pressure is so strong that it prevents additional accretion and formation of stars. Okay, so which means the fact that this has such a high surface density of star formation means that this is a system in a highly transient phase, must last very short because it cannot continue sustain this rate for a long period. The other interesting thing, however, is the detection of this water absorption line that is, as you see, blue shifted and asymmetric with this very blue wing with velocities tracing absorption, molecular gas in absorption with fairly high velocity up to 1,000, close to 1,000 solar masses kilometers per second, which is tracing essentially very massive and fast, dense molecular winds, which is being ejected by these very dense starburst, very compact starburst, which is not surprising that you have, as I mentioned, most star-forming galaxies do have, and since it is an extreme star-forming galaxy, it's not surprising that you have such a strong outflow. However, when you infer the outflow rate of this galaxy, you get, so this is the outflow rate as a function of star formation rate for a number of, in the molecular phase, for a number of local and high redshift galaxies. And you see that most galaxies follow, when you look in the molecular phase, you have a higher mass loading factor closer to unity. But when you go to star formation rates which are very high, and now with this extreme galaxy at high redshift, we are probing the outflow in the highest star formation rate ever detected, you see that this is much lower than unity. So what is suggesting this is that when you are at this extremely high star formation rate with this extremely high surface density star formation rate, the effectiveness of the outflow in regulated star formation decreases even further, and therefore the star formation just can keep going at a very high rate. You have a sort of runaway process, and therefore in this case, the starburst can deplete all of the star formation, all the available gas in less than 10 megayears. So the galaxy will become quickly passive, and unless, of course, replenished by additional gas. So this is just to tell you that you may not need actually an outflow. If you just leave the galaxy, form stars at this amazingly high rate, you just run out of gas, and the galaxy will essentially become passive simply because it has been using up all of its gas through simple star formation at an amazingly high rate. Okay. The other mechanism, however, which is more, this is a recent result which may open a different route for the quenching of star formation in high-redshift galaxies, but the more classical route, which is, as I mentioned, been invoked to explain the suppression of the efficiency of star formation at high masses, is the presence of feedback of supermassive accreting black holes, that is quasars, or more generally AGNs. And indeed, we do see that whenever you have an AGN or a quasar, these are essentially ubiquitously. I don't think there is any case, honestly, where you don't see any evidence of outflows. The radiation pressure associated with the energy injected by these the supermassive accreting black holes nearly always essentially generate a significant outflow. And these are just, there is a whole extensive literature by several groups, including here in Granada. And these are just a few examples. So you see these outflows in the molecular phase traced by the very high velocity gas in molecular gas with velocity up to or exceeding even 1,000 km per second. And you see typically these high velocities only when you have again an AGNs. With the star formation, it's difficult to achieve these extremely high velocities. And this in the molecular phase. This is an example in the ionized phase, where this green light is a nearby galaxy mapped with MUSE at the Very Large Telescope in oxygen 3. Okay, and there is no doubt that both at low luminosity and the high luminosity, you have these prominent outflows. And of course, this study of quasar or AGNs-driven outflows has been extended up to high redshift. This is just again a few examples. Again, often in the ionized phase, traced by the oxygen 3 lines, which is redshifted into the near infrared, again by finding high velocity tails of these nebula lines. Often these are asymmetric, indicating that the outflow is essentially escaping the galaxy along some preferential direction. And we also see these massive and fast outflows also in the cold and neutral phase of the gas. This is an example of a stacking of a large sample of quasars at redshift around 6, where we have used the C2 lines at 158 micron, which is redshifted, is redshift in 2 millimeter bands, and therefore we could observe it with ALMA. And you see also in this case you have these very high velocity wings with the velocities exceeding 1,000 km per second, which again indicate to you that whenever you have these powerful sources, these tend to drive these massive outflows in their host galaxies. So this goes in the direction that indeed, when you have an AGNs, supermassive black holes, especially in massive systems which typically host the most massive supermassive black holes, they do drive these massive outflows, which help to remove gas and therefore suppress star formation in the host galaxies. However, when this is all nice from a qualitative point of view, when you investigate this in a more quantitative way, you again start to run into to face some problems. Well, this is, sorry, before I run into the problems, just to illustrate you that how effective are AGNs in driving outflows. So this is the outflow rate, this is in the molecular phase, as a function of AGN luminosity. And these are color-coded by the fraction of the AGN luminosity, which is contributing to the bolometric luminosity. And what you see is that at high luminosity, the most powerful, most extreme outflows in terms of outflow rate are associated with powerful quasars with luminosity of around 10 to the 46 erg per second. You may notice that there are a number of galaxies here with which are classified as not as AGNs but as star-forming galaxies with little contribution from any AGN emission. And in these cases, we believe that these are fossil outflows in essentially cases where there was a strong AGNs in these galaxies, and you know that the AGN can have very strong variability, so the AGN can essentially stop accreting on short time scales and therefore disappear, but the outflow has time scales of million years, so it keeps moving, and so you still detect the outflow. So all of these, and this is indeed predicted by various theories. So all of these high outflow rate in galaxies without AGNs, we believe are associated with fossil outflows. Okay, but for the rest, leaving aside these peculiar cases, most of the powerful outflow are associated with powerful AGNs. Okay. However, when you quantify more in detail the physics of this outflow, what you find is that they do not seem to be very effective. So the most, and this is best seen when you investigate the kinetic power of these outflows. According to most models, to be effective, the outflows in removing gas out of the galaxy, they have to be energy conserving in the sense that the energy injected by the AGNs, it doesn't get lost into radiation losses. It keeps being associated with outflowing gas, and is doing so, it can inject a lot more energy into driving the outflow, and so it can be really effective in removing gas. In this case, this is the called energy-driven or blast wave scenario. You expect the kinetic power of the outflow should be of the order of a few percent of the AGN radiative luminosity. So this sort of, there is red line here, okay? And what you see, this is a collection of AGN outflows measured, kinetic power in outflows associated with AGNs. In most AGNs, especially the most luminous one, the kinetic power is one or a few orders of magnitude lower than what you would expect in this energy-driven scenario, which meaning that, again, this outflow don't look as effective as you would expect in this ejective mode. So they are extremely powerful, but they fail to drive the outflow at the level that it would be required to really suppress or even quench star formation. On top of this, even if these outflows, quasar-driven, reach velocities even in excess of 1,000 km per second, if you calculate what fraction of the outflow is actually escaping the galaxy, this is, which is plotted in this axis, this is actually relatively small. Only a few percent of the outflow typically leave the galaxy. Most of the gas will rain back into the galaxy and therefore will be usable for additional star formation, okay? So again, questioning the effectiveness in these AGN-driven outflows in actually suppressing or removing quenching star formation. What's happening, however, so what's likely to happen is that, again, as I mentioned for the case of supernova-driven outflows, even for AGN-driven outflows, they're extremely powerful, but they fail probably according to the, not unexpectedly, according to the simulations, 3D simulations, they fail to couple very well with the dense gas in the galaxy. The dense gas tend to be self-shielded, and all the energy that is being injected by the AGNs tend to leave again the galaxy, the ISM, through the direction of least resistance. Okay, typically, if you have this galaxy again, as it was for the supernova, most of the energy injected by the AGNs will leave the galaxy perpendicular to the disk, and therefore leaving most of the gas in the galaxy unaffected, and leaving into the circumgalactic medium, which means that the ejective mode, that is the mode in which the quasar is supposed to remove gas of the galaxies, is again not not that useful to suppress star formation. However, this is not the end of the story, in the sense that it's not that the AGN is harmless. What it does, all of this energy which leaves the galaxy, goes into heating the halo of the galaxy, the circumgalactic medium. Heating the circumgalactic medium means that it suppresses the accretion of cold gas onto the galaxy. So if you keep the halo hot, you will at that point prevent fresh gas to reach the galaxy and to provide additional fuel for star formation. So you enter into a mode where the galaxy is being isolated for further accretion, and therefore the galaxy can keep forming stars as long as it has gas available in the galaxy. But at some point, when it uses up all of the gas through star formation, it will essentially starve. It will not have additional gas for continuing. And therefore, this is a way which we think is the so-called quenching by starvation, sometimes also referred as delayed, because the effect is delayed feedback, because the effect is delayed in terms of star formation, or preventing, because it prevents further star formation into the galaxy. Okay, it's similar to sometimes what is referred to as radio mode, but associated with radio jets. In this case, the heating of the halo is due to the injection of energy by the radio jets. But is now commonly believed that the same effect can be associated with wide-angle outflows. Okay, so a scenario that can possibly hold is that in a galaxy you have star formation and accretion of gas when it is in sort of a steady state, but the AGN outflow can, of course, have an injective effect on the immediate vicinity of the black hole of the AGN, say the region of the bulge or so, and can indeed be effective in remove locally gas, and therefore be effective in this ejective mode in the vicinity, in the central region of the galaxy. But it doesn't suppress remove gas across the entire galaxy. The rest of the disk remains little affected. But what it does is start to inject energy into the halo, and you start having this very hot halo, and therefore you at some point you stop the accretion of further gas, and therefore the galaxy starts to starve, and therefore start to quench as a consequence of starvation. Later on, you can also have the effect of further injection of energy by radio jets, and therefore you have this sort called maintenance mode, where the galaxy is kept sort of passive and quiescent as a consequence again of this continuous heating of the halo. Now, to investigate, to probe this starvation scenario, this heating of the halo by AGNs is very difficult, especially at high redshift, where you have where the bulk of this action is expected to take place. But there are some methods to do this, some of these indirect and some of them direct. One of these which we have been exploring in Cambridge is by using the stellar metallicity to explore these galaxy quenching scenarios, and in an indirect way, but in a very effective way. And this sketch tries to illustrate to you how you can use this information to infer information of the quenching and feedback in galaxies. So if you have, so this is a diagram where you have stellar metallicity as a function of stellar mass. So if you have a galaxy which is in a steady state where it is accreting gas from the intergalactic medium and forming stars, what happens is that as the galaxy forms stars, it increases the stellar mass, of course, and increases, as it's been the new generation of stars inject metals into the ISM, it increases the metallicity, and the new generation of stars have, of course, higher metallicity. But the increase in metallicity is relatively modest, because you keep having inflow from the intergalactic medium which dilutes the metallicity, because the inflow from the intergalactic medium is nearly pristine or low metallicity. Okay, so the increase in metallicity is high. It goes increases, but not at a very high rate. If at some point you have a removal of gas by outflows, what happens? You stop star formation because you remove the gas, and what you have is that the galaxy will essentially result into a passive galaxy, and which will have the same stellar mass and the same stellar metallicity as the star-forming progenitor. Okay, just the galaxy stays there. Now, in the case of quenching by starvation, that where you stop the accretion of gas, so what you have is that, again, in the phase where the galaxy is accreting gases, you increase the stellar mass and the stellar metallicity by a small amount. But at some point, if you stop for some reason the accretion of gas, for instance, through this heating of the halo, what happens is that the galaxy keeps forming stars with available gas, and in this phase, you don't have any longer dilution of the metallicity from the intergalactic medium, and therefore the metallicity in this case increases much more steeply. So the result that you have is that a passive galaxy, which is once all of the gas is finished, is used up, which has a stellar mass slightly higher than the star-forming progenitor, but most importantly, a stellar metallicity which is much higher than the star-forming progenitor. Okay, so you have a gap in stellar metallicity between the the resulting passive galaxy and the star-forming progenitor. And you can explore these statistically by using the stellar metallicity of local passive galaxies and compare it with their star-forming progenitors at high redshift. And as you see, there is a systemic, again, this is stellar metallicity function of stellar mass, the same diagram that I had shown you here. When you do these are observations, are not simulations, are actual measurements of galaxies. What you have is that the metallicity of local passive galaxies has a significant gap with respect to their star-forming progenitors, meaning that as I mentioned, this gap in metallicity is a clear indication that the quenching of this system has happened through an extensive phase of starvation. So it's an indirect way to probe that indeed this quenching has primarily happened through a starvation phase. Now, of course, you would like to probe directly this starvation mechanism, which is this heating of the halo, but it's not easy because you would like to probe the hot halo in these galaxies possibly associated with AGNs at high redshift, but this is not possible. Probably maybe because of course the ideal would be to probe these in the X-rays, but current facilities cannot probe these diffuse hot halos at high redshift. Maybe with Athena, with the next generation X-ray facilities, it will be possible. But for the moment, one method to probe these hot halos is by using the Sunyaev-Zadovich effect against the CMB. Okay, where you expect to see a depression, an effect of absorption at low frequencies in the around 100 gigahertz as a consequence of the Sunyaev-Zadovich effect against the CMB. And this is something which people have been trying to see. This is an attempt done by stacking together thousands of data from CMB experiments from Planck, the Atacama Cosmological Telescope, and Herschel, trying to detect this signature of Sunyaev-Zadovich by stacking together thousands of quasars. The problem is that the beam of these experiments is so large that you have a lot of emission from the quasar itself and from the surrounding star-forming galaxies. So you have the bulk of the signal is this bump of emission in the far infrared and some millimeter associated with the star formation in these systems. And of course, people what have tried to do is to model this emission to detect the signature of the underlying Sunyaev-Zadovich effect, and they claim that they have reached a 2-4 sigma detection of this heating of the halo around quasars. Is of course tentative. Of course, the better way would be to directly resolve the hot halo from the emitting regions, and that's what we have tried to do. So to use ALMA in this case, where ALMA is very effective because it can probe both large scales and resolve out the emitting sources. And we have started to detect signatures at the level of 3-4 sigma of synovial absorption at low frequency, associated possibly with the heating of individual quasars at high redshift. These are preliminary results, but we have got more time to explore this edge effect in high redshift quasars to probe the halo heating at high redshift. This is just to show one last thing about this, that is not only about gas content in terms of quenching. We have been also investigating the star formation efficiency, and have found that this is the lack of gas is not the only reason why galaxies leave the main sequence, but also an effect of the efficiency with which the gas forms stars. So this is a work of a student, Joanna Petrovska in Cambridge. This is again the diagram of star formation rate as a function of stellar mass. And here you have the main sequence, and so you have the quiescence sequence here. And these are galaxies which are color-coded by the gas fraction. I can come back to you later on how the gas content is measured. But you see that, as expected, as you move away from the main sequence, the gas content gets lower. And so this is one of the reasons why these galaxies are have reduced star formation rate. However, we can also measure the star formation efficiency, so the star formation rate per unit gas mass. And you see that also the star formation efficiency decreases going towards the main sequence. So away from the main sequence and towards the quiescent region. So it seems that the reason why the galaxy leave the main sequence and stop forming stars or reduce their formation of stars is not only the lack of gas, because they're possibly starving, but also because the available gas gets less and less efficient in forming stars. And why is this? And the two effects have a similar comparable role. That is, half of the effect of the quenching of star formation is due to the lack of gas, and half is due to the fact that the star formation efficiency is lower. And why is that the star formation efficiency gets so low leaving the main sequence is one of the open problems that we are trying to investigate. Do I have still 5 minutes or? Okay. So the last bit that I wanted to discuss is, so far I have been discussing the effect of negative feedback of outflows. But recent work that have been done by various groups, including ours, is that outflow can also have a positive effect on their host galaxies in terms of star formation. Now, there have been in the last few years examples of star formation induced or fostered by jets of outflows in some galaxies. This is Centaurus A is one of the most famous examples. It has a powerful radio jet, and on large scales we do see evidence for star formation which is due to the gas in the circumgalactic medium or even in the galaxy compressed by this the shock, and as a consequence compression actually triggers the formation of stars. This is an example of a cloud observed with the instrument MUSE, which is in the vicinity of the jet, and where the study with the MUSE has revealed the presence not only of shocked gas, but inside the shocked cloud, the presence of a very young regions of star formation detected through the so-called BPT diagrams. But even more spectacularly, you see these filaments of very young stars. This is an image with HST where you see the individual OB stars which are being formed parallel to the jet as a consequence of compression of the jet expanding into the intergalactic medium. And this is one of the most beautiful example of triggered star formation by an outflow or ejective, where you actually see the individual stars being formed at the edge of the parallel to the jet. The only thing is that this effect is modest. The star formation rate is the order of 0.1 to 0.5 solar masses per year. So it's not that it seems to be contributing significantly to the evolution of the galaxy, although it's an interesting effect. At higher redshift, there's been claimed an even more prominent effect of this compression of the gas. This is one work by, again, our team, where associated with the high redshift quasar, where through the oxygen tree line we see this fast outflow channeled into a direction of the galaxy. And by mapping the H alpha, we can trace the star formation in the galaxy. And star formation seems to be fostered in the regions surrounding the jet, which is probably has been interpreted as compression again of the outflow on the ISM of the galaxy, which is, as a consequence of compression, is fostering star formation in the host galaxy. And in this case, the star formation rate, the induced star formation rate, is much higher, the order of 200 solar masses per year. However, all of these cases of positive feedback is gas or in the galaxy or in the circumgalactic medium, which is being compressed by the outflow, by the jet, and therefore which result in the new star formation in the host galaxy. However, there's been more recent models where they suggest that star formation can happen inside the outflow. So essentially, we have seen that there is a lot of molecular gas inside the outflow. This molecular gas can undergo cooling and fragmentation and form stars inside the outflow. And this is quite different from the previous scenario, because if stars from inside gas, which is leaving the galaxy at high velocity, then the newly formed stars have the kinematic imprint of the outflow. That means that they form at high velocity on radial orbits. And this, if the velocity is higher than escape velocity, the newly formed stars will leave the galaxy. If they do not reach the escape velocity, they will start to oscillate around the center and therefore become part of the spheroidal component of the galaxy. Okay, so the implications are quite dramatic in the sense that you could have a fraction of the spheroidal component of galaxy, the bulge, or the halo, or even the elliptical galaxies formed through this mechanism. And there have been quite several models recently which have been claiming that this mechanism can be in place. And this would be a totally new mechanism for forming stars and galaxies. Now, it may sound a little bit far-fetching, but actually when you look at the properties of these galactic outflows, you see that it's not such a crazy idea, because not only these galactic outflows have a lot of molecular gas, but this molecular gas in the outflow is very dense, as traced by traces of dense molecular gas such as HCN. As you see, even HCN has a very broad wings with very high velocity gas. And not only, the fraction of dense gas in the outflow is even higher than in the host galaxy. So in the outflow, you have even more dense gas than in the host galaxy. And not only, this dense gas is very clumpy. So you have dense gas, clumpy, which is exactly the condition that are found in galactic star-forming regions. So you wonder why this gas in the outflow shouldn't form stars. Actually, you do expect this gas in the outflow to form stars. This is just to show you that even in the optical, we see now that the bulk of the gas in the outflow, based on the optical nebula lines, is actually denser than in the host galaxy, which means that essentially this gas is being compressed and is collapsing and probably undergoing gravitational collapse. Now, to test whether these outflows are really forming stars, we have undertaken, not only us, but also other groups, programs started to investigate the physical condition of the outflowing gas. And what we have found, for instance, is that in a recent survey, that about 30% of the outflowing gas in these galactic outflows, the outflowing gas have diagnostics typical of star-forming gas, suggesting that indeed the good fraction of these galactic outflows do host star formation. And we have confirmed these not only with the classical BPT diagrams, but also with the additional near-infrared diagnostics, which are even more less affected by other degeneracies. Of course, it would be nice not only to have diagnostics of those information, it would be nice to see the stars formed at high velocity in the outflows. And that's what we have achieved recently. This is our observations. To see the young hot stars forming the outflow, you have to go to the UV because that's where you have the bulk of the emission from young stars. This is an observation with the Hubble Space Telescope with COS, which is a fantastic spectrograph of a galaxy which has a prominent outflow, a Euler with a very fast outflow, this Iris galaxy. And this is the UV, the COS spectrum of the galaxy. And you see all of these lines this is not noise, these are all absorption features associated with ISM in the galaxy. And all of them are blue shifted, simply confirming that indeed you have this prominent outflow in the galaxy. And that's nothing new, it's simply confirming that you have the outflow. But this carbon-3 line, this is a pure photospheric feature of OB stars, and it's an ambiguous tracer of the kinematics of the OB stars. And as you see, you have that this feature is blue shifted by 300 km per second, and there has also a secondary dip at 1000 km per second, which is telling you that these stars in young stars have the same velocity as the gas in the outflow, which is essentially an ambiguous proof that stars have been formed in the outflow of this galaxy. You may say, okay, this is all interesting, but what about the Milky Way? If this was a mechanism if outflows is a mechanism for producing stars associated with the spheroidal component of galaxy, why don't we see these stars formed in the outflow in the Milky Way? One possible explanation is that not all galaxies go through this phase, and also the black hole in our Milky Way in our galaxy is so small, and therefore the outflow associated with when it was active may not have been powerful enough to generate this effect. However, this is actually in the end not true, in the sense that there's been a very recent release of the Gaia results for tracing the properties of the stars in the halo of the galaxy, and what this this team has found with the last Gaia release is a population of stars. So this is a diagram of the azimuthal velocity. So these are stars in the 5 kiloparsec around the solar neighborhood. This is the azimuthal velocity is a function of age of the stars. And so these are stars associated with the thick and thin disks. And these are stars in the halo which have very high radial orbits and are very metal rich. You know that most of the stars in the halo have random orbits and metal poor. This is a substantial population of stars which are essentially oscillating around the center of the galaxy, and they are very metal rich. And this is exactly what was the expectation of these models of stars formed in the outflow, that they should have formed from the central region of the galaxy, where you have high metal enrichment, and formed on radial orbits that becoming part of either the bulge or the halo. And this is exactly what Gaia is finding. And also is showing that they can also trace the age of these stars, and you see that most of these stars on radial orbits, metal rich, actually formed in our galaxy around redshift 1, between 1 and 4. So the next goal is to see this phenomenon in place at high redshift through next generation of instruments such as the Extremely Large Telescope and GWST. But certainly this seems to be a new interesting channel for forming stars in galaxies, especially for what concerns the spheroidal component. And this is the summary. I would leave it here because I think I have overrun, and I'm open to questions. Thank you.
questions?
It's a pleasure, this talk. Thank you very much. In the very last diagram that you've just shown, so is everything at V phi around 0 can be considered radial orbits? Not just the old, so basically there's this dashed line around 0. So if I understand rightly, this is radial orbits.
Yes, well,
okay.
This is just one of the diagrams that they have in this paper.
Because there's a splash around 1 giga. Would nicely agree with a recent finding of ours that there was a massive star-forming event about a giga-year ago at the center of the Milky Way. So that could have created a huge outflow, and apparently there's stars of a giga-year age on radial orbits. So would that be a valid interpretation, or is that complete nonsense what I'm saying? If there were a massive outflow a year ago, could that have been responsible for that dark spot? Not the very dark one, but around at 0 at 1 giga-year of age. Yes.
To be totally, it's still essentially an open field. There is the alternative interpretation of this is that you had a head-on collision of another galaxy exactly towards the center of over the Milky Way, and that may have produced also radial orbits, which is
right. That's basically the last major merger.
Could be a possibility. I personally find it more unlikely because for two reasons. First, most of the merging events have some angular momentum. So having exactly zero angular, so these stars essentially have zero angular momentum, and which is unlikely to have in any kind of way. Secondly, these are relatively metal-rich stars. If you had, so you would have a sort of a conspiracy that the merging galaxy would have had relatively high metallicity. So it's, but in principle, the same team is looking into other tracers to discriminate between these scenarios. Yeah.
Hi, this is a very nice talk. Thank you. Well, I have several questions. I will start with the relation, the stellar mass metallicity that you saw, where you compare the high-redshift galaxy with the more nearby galaxy. Yeah, so that means that there is the main problem, apparently here they show a strong evolution of the mass metallicity relation, but my main problem with this is how has been estimated the stellar metallicity in the high-redshift galaxy.
This is indeed a problem because, well, first you see that there is an offset already by comparing with the local star-forming sequence. Okay, so these are essentially measured with the Sloan spectra and with different kind of either indices or full spectral fitting, whatever, but in a consistent way with the passive. Okay, and you see that there is already an offset. And so if you go at high redshift with the progenitors, this offset can only increase because you know that the mass metallicity relation at high redshift becomes more metal poor. Okay, so this is already, you already have an offset here and it can only get higher. Now the way we have estimated this is since the measurement of the mass metallicity relation at high redshift is more difficult, we have used here the gas mass metallicity relation because for the young stellar population, they should have the same metallicity as the gas out of which they form, although there must be an offset of 0.1 or 0.2 dex. However, having said that, there's now a nice measurements from the Vandals team and also other surveys where through stacking, they have the mass metallicity relation for young stars, for the young star population at redshift around 3, which is about the redshift of the progenitor of this local passive, and is essentially consistent with what derived here. Now, I've made a long story short, but this, of course, is again another of these 15 pages paper where this is, discussed more in detail. Yeah.
So that means that in reality, there are involved several difficulty, which is, for one hand, you are estimating the stellar metallicity from optical spectral data, spectra in particular, which is from the slow, and the other is coming mainly from the gas, ionized gas.
Even if you use the stellar metallicity, which are from the continuum, which is proper stellar metallicity, they agree with this line. Of course, you have fewer points here. You have just target points, but it's consistent.
To be the ultraviolet continuum.
The continuum and the Doppler. But let's say if you take these population here, these are measured with the optical. These are already offset. Okay, you already have the gap here, and this offset can only increase with redshift because if you're these local starforming galaxies are not the progenitors of this passive because are at low redshift, of course. Okay, well these are several gigayears old. So if you take how this star-forming sequence evolved at high redshift, master can only decrease. So the gap can only increase. So if you wish, you can simply take this gap here between which are fully consistent. Okay. But can only increase the gap.
Also, I didn't understand well if the carbon-3 line that you have detected in this Iris galaxy, you say that is from the wing of massive star, or it is in the stellar medium?
So it's indeed photospheric. So it's pure photospheric. And indeed, it's often used as in dwarf as a rest frame reference in COS spectra. Is used as to define the rest frame. And anyhow, to measure as a template, we have used the COS spectra of galactic OB stars. So it's just the.
This is the only one. The sphere line that you said.
The deepest is the deepest in the.
But I understand that
we don't have the others in the spectrum because the other OB star features are at shorter wavelengths, longer wavelengths, and are not in the spectrum. Actually, there is another one which is nitrogen 4, but that's has a broad preceding profile, so it can't be used for kinematics in the OB stars. There are other two which are fainter, but are not in the spectral range, and so we can't probe them. But anyhow, even if we had that region, you see that it's clearly detected C3, but not at signal to noise of 30. So I suspect that the other lines would be maybe too faint to detect.
Because usually I remember when I studied the starboard galaxy, is that what you found is that there is an interstellar line which is really blue shifty, in the same way as the wind line in carbon-4, silicon-4.
Associated winds, so are all silicon-4, carbon-4, those are all P-signaling profile lines which are affected by the winds of the OB stars. This is the only line which is one of the few lines that is purely photospheric, not associated with the winds, and that's why it's being used to trace the rest frame of the young stellar population in galaxies. If you look at James and these other studies, which we all use COS spectra, they use this line as a tracer of the rest frame typically of the galaxy, which is indeed consistent with what found in other optical lines of the galaxy, of the older stellar population.
Thank you.
Just for you to know, at this afternoon, starting at 4, we can follow up the discussion. I mean, a detailed discussion on everything you like, because we will have an open session in Building C. Okay, so just for getting more in details of anything you like to know. And then at the end of this colloquium today, there will be an informal discussion as well with young researchers, as you all know. Okay. Any other question? I have just a short one. So, as far as I understood, what you're saying is that outflows are not enough to explain, either from AGN or from star formation, not enough to explain the very first plot you showed.
Not enough. They are not effective in the ejective mode. So the simply removing is probably not enough to explain that. But their effect in heating, injecting energy into the halo, into the circumgalactic medium, that's probably very effective in a sort of a delayed quenching, delayed feedback. That's probably, that's what also many simulations now seem to show.
So thank you very much again, and